we want to look at how we can find the enthalpy of an unknown reaction using something called standard enthalpies of formation. And we'll talk about what those are in a second. But just to review, in the normal form of Hess's law, we saw that when we add two reactions together, we can add their enthalpies to find the enthalpy of an unknown reaction. So in this example, if I add these two reactions together, I'm going to get N2 plus 2O2 makes NO2. And if those reactions add up, then the enthalpies will add up to give me the enthalpy of the overall reaction. So these two enthalpies would add up to give me an enthalpy of 68 kilojoules for this overall reaction. We're going to use the same concept, but we're going to use reactions that are standard. So if we don't have any reactions given to us, we can still find an enthalpy for another reaction. So before we actually get into Hess's law, we want to just look at what standard enthalpies of formation are and what formation reactions are. So before we can actually use formation reactions, we have to know what they are. A formation reaction basically is just a substance that's being formed. So it'll be in the products from its standard elements. We'll do an example down here, but basically we want to make 1 mole of a substance from its standard elements. So we'll write some standard enthalpy of formation. We'll write the formation reactions to start. And to do that, we'll look at what we're writing the formation of, and we'll start off with writing 1 mole of that substance in the product. So we just want to make sure that we include the coefficient 1, the substance that they've given us, and we want to include the state that they've given us. So they said that this was solid, and we'll include solid. And then the next step is we're going to write all of my reactant elements. So I'm just going to go through and write like every atom. I'll start with the C, and then H, then O, in their standard state. So how do we know our standard states? Look at the periodic table. This is the same periodic table that you have in the back of your textbook. The ones that have black lettering, so not the color of the box, but the lettering, if it's black, those are solid. So carbon is my first element that I'm going to start off with over here, is solid. It is black, the lettering. I'm not going to worry about balancing at this point in time. I'm just going to list each element in its standard state. Then the next element is hydrogen. Now be careful, it is a gas because it's red lettering. Red lettering is gas. Blue lettering in the periodic table that we have in the back of our textbook is a liquid at standard temperature. But just be careful of our diatomic ones. I like to call them Haberfinkels. You might have known them as a hockey stick or another name, but they're the diatomic elements H, O, Br, F, I, N, and Cl. So we're going to write our next element. We did C, we're going to do H, but because it's a diatomic, I'm going to include it as H2 gas. And again, don't worry about the balancing just yet. We'll look after that in our last step, we'll do the balancing. Last substance that I need is oxygen, and it is also diatomic, so I'm going to write it as O2, and it's red on the periodic table, so I'm going to write it as a gas. Two other ones to look out for besides those diatomics are sulfur, which comes as S8 in the solid form, and phosphorus, which comes as P4 in the solid form. So that's just the molecules that it likes to make when it's an element or just that one atom, because it would be unstable if it was just by itself. And we're almost done. We just need to balance so that we get the right numbers in our products over here. So my first element, I need to have 6 carbons in the products. So I want to make sure I have this balanced for 1. So I'm going to make sure I have 6 in my reactants. So I'm going to put a coefficient of 6 in front of the carbon. And for hydrogen, I have to get 12 in the products. I have 2 in my reactants. So if I multiply the reactants by 6, that will bring me up to 12, and my reactants and products will balance. Lastly, 8 is 0.6, so it's going to get a coefficient of 3 in the reactant side, so that'll be 6 oxygen as well. And you are done your formation equation. Let's just try one more. So for this next substance, we are going to do the same thing. We'll just take our product and put it in the product balanced with 1 mole. And you just want to double check that you keep that state the same. Then what we'll do is we'll start off with every element and add them. Start with sodium, sulfur, and oxygen. And this might seem counterintuitive. When we split ionic compounds up once they're formed, they always split into their ions. But this isn't splitting up an ionic compound. It's actually forming it from the elements. So it is different than our normal reactions where we split up the ions. So we want to form from elements. Sodium is solid on our periodic table. So I'll start with solid sodium. And then my next element to make this compound is sulfur. So just watch for these ones right here, this list right here. I have to watch out for the diatomics S8P4. So I am going to use the standard form of sulfur, which is S8. And lastly, oxygen is my last element. I'm going to use O2 because it is a diatomic. And oxygen is a gas. It is red on my periodic table. The lettering is red, so it is a gas. Well, the other 2 are solids. I'm almost done. I just actually have to balance this by changing the reactants coefficients so that they will balance out with my product. And sodium, I have 2 in my product, so I'm going to add a 2 to balance that out in the reactants. Now, when we have these diatomics and S8 and P4, sometimes we'll have to add fractions to make it balance, which is perfectly fine. We want to keep a fraction so that we have the 1 mole of the product. So that's our first thing that we want to do, is always ensure that we have 1 mole of product. So for sulfur, I only need 1 sulfur. They come as S8, so I'm going to have a fraction of sulfur, and I'm just going to have 1/8 of S8, so it will give me 1 sulfur. Oxygen, I need 4. On the reactant side, I only have 2, so I'm going to double that and have 2 times 2, and it'll give me my 4. And that's how I write my formation reactions. So we want to be able to use these reactions to find the enthalpy of an unknown reaction. These formation reactions we can add together. And the reason we can do that is because there are tables with many, many enthalpies for every formation reaction that are in the table. So if it lists the substance, it'll give the enthalpy of that formation reaction. It assumes that we could write the formation reaction for NH3, and then this would be the enthalpy for 1 mole of NH3, or for this reaction where we've balanced it for 1 mole. So we have tables of these. They're very useful because then we can find the enthalpy of lots of reactions that we wouldn't be able to find the enthalpy of. All of these tables they've reported all of the heats for what's called standard ambient temperature and pressure. So 25 degrees Celsius and 100 kilopascals. So this heat has a little circle up here. It's called a knot. The little circle, it looks like degrees, but it's actually a knot in this case. And that means it's at SATP, or standard ambient temperature and pressure. And these are the tables that we're going to use to find heats of other reactions. So we're going to take these formation reactions and the heats of them to find heats of other reactions. The other thing to notice in this table is that if you have something in its standard form, you're not actually forming it, because by definition, a formation reaction is to start with an element in its standard form. If it's still in its standard form, there's been no reaction. So on these tables, depending on which table it is, you'll see that some compounds have 0, or some elements actually have 0, and that's just because it's in its standard form. And if you don't see it on there, you'll have to remember that if it's the standard form O2, it would be 0. So now that we know what those standard heats of formation are and the formation reaction, we can actually use them to find a heat of an unknown reaction. So in our first question, ethanol is the same type of alcohol found in alcoholic beverages, and it's also found in fuels. Ethanol can be burned to make 3O with oxygen to make carbon dioxide and water. So we want to find the enthalpy of this reaction, and we'll do that using our equation up here. So this equation is, I will point you to some other videos that derive it. Just to make this video not too long, I'm not going to derive it here. But when we add up our formation reactions, if we add up the positive version of the products, and then if we flip the reactions for the reactants so that the compounds are in the reactants, we can find the delta H for a target reaction. But we do have to add up each of the heats of formation for the products. And this funny symbol here is sigma. It just means take the sum of all of the heats of formation of the products. There is one part of this reaction we haven't talked about. It's this number of moles here. That is the number of moles that would be reacting in our reaction, which is the coefficient in the balanced chemical equation. So remember when we did our thermochemical reactions, we said that the number of moles reacting were 1 if there was a coefficient of 1, 3 if there's a coefficient of 3, 2, 3, and that's what our enthalpy is for. So we're going to use those number of moles. So we'll do that for our products. We'll use our tables to get all those heats of formations. We'll be able to find the number of moles from the reaction, and then we will subtract all of the heats of formation of the reactants. I'm just going to pull over a table so that we can look at the heats of formation. The other thing I'm going to do, when we have a compound written out like this, where CH3, CH2OH, they do write that because it's a little bit of a clue to the structure of it, but we often want to just put it together. So I'm going to collect my C's. There's 2 of them, C2. I'll collect my H's. There are 6, C2H6. O is another way of writing ethanol. So we might need to look for something similar to that on our data tables. So I pulled over a data table that was, I just found online. Ours might have slightly different numbers. Sometimes they report them differently, but we'll still do the problem the same. So what I do is I'm going to do all of my products and add up my products over here, add up the standard heats of formation for both, and I'll multiply by the number of moles, which is the coefficient. So I'm going to start with carbon dioxide, and I'm just going to, that sigma here just means take the sum of all of those. So I'm going to take 2 moles for carbon dioxide because that is what is in the reaction as a coefficient. And then I'm going to look up, this is a bracket, it's a little bit hard to see. I'm going to look up my standard enthalpy of formation for carbon dioxide. Make sure you check the state. Carbon dioxide gas, that's going to be negative 393.5. And the units are kilojoules per mole. So when we actually multiply it by 2 moles, the kilojoules will cancel out. And then I'll add in my next term, which is H2O. I'll have 3 of those and 3 moles of those. And then I want to look for my heat of formation for my table for H2O. And if I go over here, there are actually 2 H2O values. So be careful with H2O. This is H2O gas. So I'm going to come over here. H2O is at the bottom. So I'm going to actually use the H2O gas, the negative 241. So be careful if you are off by a little bit in your answer. Often you may just have picked the wrong. You might have picked the wrong value for H2O because it can be different depending on if it's a liquid or gas. So I'm just going to put that in there, 241.8, and we're ready to do our reactants. So for our reactants, we'll have to subtract all of them. So this is why I use my big square brackets, because when I want to add everything up, they need to be in brackets. And then I'm going to subtract all of my reactants, which will also be in brackets. So now we'll move on to our reactants, and they do need to be subtracted. And I do have to take the sum of all of the reactants as well. So I can start with my ethanol. It's right here. They wrote it just slightly differently. They have C2H5OH, and it's negative 277.7 kilojoules. We just have 1 mole of it in our balanced chemical reaction. And then my last term. So just be careful with your brackets. We want to subtract all of the reactants added together. So I put those big square brackets so that we take the sum of all those reactants, and then we do the subtraction. I'm also going to add oxygen. So if I come and look over at my table, I don't have oxygen. So I don't have that delta H, not F. And sometimes people get stuck in like, what am I supposed to do? So just a reminder, if you have an element in the standard form, you actually don't have to include it because there is no heat of formation. It's already in its standard form. So it would be 0. You don't necessarily have to write that 0 in. I'm just putting it in to remind you that this one here is going to have a 0 heat of formation. So just be careful of those. Once I've done that, it's basically following some good bed mass rules so that we do our brackets first, and then we can do our subtraction. And we have to multiply in the brackets first. So let me actually multiply the 2 times my 393, and we'll simplify this a little bit. We'll also do the 3 times the negative 241. And when we multiply the first term, we get negative 787. My units will be just kilojoules because I'm going to cancel out the moles on the bottom and the top because I have 2 moles multiplied by kilojoules per mole. So I'll just be left with kilojoules. And the same for the second term. The moles cancel out, and I will be left with kilojoules. And then we can subtract our reactants, which are in red. And then we'll just add and subtract all of those numbers. And when we do, our final answer is negative 1, 2, 3, 4.7 kilojoules. So we found the enthalpy change for a reaction that we didn't know the enthalpy change of, the combustion of ethanol up here. And we used our formation reactions, which we had standard formation reactions tables, and it was a fairly easy way to figure out the heat of an unknown reaction.